I'm curious, what is the view on your side?
So I can see you and the slide.
Oh, all I
So,
can see. Okay.
so I'll switch it now first to the gallery view and the slide.
Okay. Hmm.
So Kohi has signed in.
Yes. All right. So, Will, should I broadcast it now?
Go ahead.
Okay. So we'll be on broadcast.
So cool. So it seems like people are coming in, and it's 1 minute before the time. So, and just to inform everyone, we'll start promptly at 8 p.m. Eastern.
Good morning, Sir Joey.
Oh, hi.
Great. Good morning po.
Yeah, thank you for participating.
Yeah, you still look so young, sir. Where are you? Are you in the States or in the Philippines?
In Maryland.
Maryland. Hi, gang. Ano mo muna ako.
Awesome. So It seems like we have majority of our speakers today. We would be starting fairly soon. It seems like we now have 89 participants. 90, it's actually still growing. Really awesome. So we have 90, 91. We have to wait for it to slow down a little bit. All right, so it looks like we're slowing down in terms of people still coming in. So I think we'll go ahead and get started. Okay, hello everyone. My name is Cynthia Garcia Idel. I'm on my third year of my PhD program at the Department of Earth and Environmental Sciences at the University of Illinois in Chicago. I'm also the press relations officer of the Philippine Engineers and Scientists Organization. I'm happy and thrilled to welcome each and every one of you to our webinar on addressing the climate and environmental crisis, especially our celebrating Joey and his 80th birthday. So to mark the momentous occasion of Joey turning 80, we are highlighting studies that have led to a greater understanding of the state of our climate and environment. These are from changes that are happening in the polar regions to topics on Philippine conservation and sustainability. We're really heartened by the response that we have received, and we're very grateful that we have all of you here today. So currently we have 106 participants currently listening, and we also welcome our audiences watching live via our YouTube live stream. We're also grateful, and I have to mention our partners, of course. We have our partners, namely the Philippine-American Academy of Science and Engineering, or PAASE, the Institute of Environmental Science and Meteorology, or IESM, at the University of the Philippines in Diliman. We have the School of Environmental Science and Management, SESAM, at the University of the Philippines, Los Baños, and the Philippine Engineers and Scientists Organization here in Chicago. We, of course, are also very thankful to our 11 outstanding speakers who graciously agreed to share their research with us today, some of which are in collaboration with Dr. Joey Comiso. Right. So I'm sure that you have seen our program today, but just to give a quick summary of what's going to happen, we have a total of 11 talks, each running for 15 minutes with a short break. It's a 5-minute break after our 5th topic. The lines, as you come in for our participants, now we have 112 participants. The lines will be automatically muted for you guys throughout the whole webinar. But we enabled the Q&A and chat features found at the bottom of your screens, so you can type your questions, your comments, or your birthday messages for Joey. We will do our best to collect and collate all of your questions, and we'll send them to the speakers so they may address your questions directly after each talk. Today's webinar will also be recorded, which we plan to post on our website later on. Also, if you're having any problems with the sound, please let me or Gay Paris know via chat. Okay. So to officially start our program, we will have Dr. Gay Jane Perez. She's an associate professor from the IESM of the University of the Philippines in Diliman to give us her welcome remarks. Go right ahead, Gay.
Hello, everyone, and welcome to our webinar. Today is a celebration of life and science. As our celebrant, Dr. Joey Comiso, celebrates his 80th birthday, we are also celebrating the many years that Dr. Comiso has gifted us with the science that led to a better understanding of our planet's climate and environment. As a senior scientist at NASA Goddard Space Flight Center, his studies focus on the polar regions where early climate change signals are expected to be detected. He developed algorithms that convert satellite data to geophysical parameters that he used to create long-term records on ice concentration, surface temperature, cloud cover, and chlorophyll-a concentration. He studied sensible and latent heat polynyas and their role in deep ocean convection and bottom water formation. Dr. Joey Comiso was among the first, if not the first, to report a dramatic decline in the Arctic perennial sea ice cover and accelerating warming in the Arctic that have provided unequivocal indicators of climate change. His contribution to science is embodied through the numerous publications and citations of his work. In fact, he only gave us the permission to announce that he's turning 80 when I reminded him that his H index is greater than his age. I was very fortunate to have met such a prolific scientist in the early stage of my scientific career. He got me started by analyzing MODIS data to understand the trends and variability of Philippine vegetation, which has further developed to our current studies on agricultural drought. We also use satellite data to associate the record high sea surface temperature with the development of Typhoon Haiyan, which is one of the strongest typhoons that hit the country. Coming to Goddard as a postdoc, I witnessed Dr. Comiso's dedication and passion for research. Despite being close to retirement, his activities are not dwindling down. On the contrary, he has served as coordinating lead author in the iPCC chapter on cryosphere. He's being invited to give talks here and there, and he's publishing more papers as ever. As a Filipino-American scientist, Dr. Joey Comiso is awe-inspiring. He is one of the founding members of the Philippine-American Academy of Science and Engineering and has served the Academy as president and members of its board of directors on several occasions. Who would have thought that he will be one of the founding members of the Philippine Geosciences and Remote Sensing Society many years later? These exemplify his utmost commitment to advance the science in the country. As a Balik scientist, he collaborates with local scientists in research on smart agriculture, forest cover change, pollution, extreme events, and the detection of fish schools. This has also been a platform for him to mentor the younger generation of scientists today. Today, his engagement continues as he advises us in the early stages of the Philippine Space Agency. This webinar is meant to celebrate Dr. Comiso's scientific contributions by highlighting studies, some in collaboration with Dr. Comiso, that have led to a greater understanding of the state of our climate and environment. It is a fitting conversation considering what's happening around us with fires in California, frosts coming earlier, hurricanes and typhoons stretching across the Atlantic and the Pacific. And oh, did I forget to mention the pandemic, which is the reason why we have this seminar online. We are very grateful to our speakers who indulge us with their time and their willingness to share their expertise despite their hectic schedules and possibly losing some sleep. I am sure you are all excited to hear from them. So without further ado, let's begin with the talks. Thank you for your participation.
Thank you so much, Kay. And so now we are at 146 participants currently listening to us through Zoom. Also, we have, of course, our YouTube audiences that are live streaming currently. So we will now start with our exciting series of talks with Dr. Claire Parkinson. She's a climate scientist at the NASA Goddard Space Flight Center, where she has worked since July 1978. Her research has centered on studying sea ice and climate change using satellite passive microwave data and, to a lesser extent, computer modeling. Today, she will talk about a satellite record on Arctic sea ice. Go right ahead, Claire.
All right, and I'll click on share screen, and hopefully that will work here. Can you see my screen now?
Not yet, Claire.
How can we see it?
Tell me when you can see it.
Can you try it again, please?
Okay. Well, I'm trying it. Okay.
There you go. Yeah.
You can see it now?
Yes, Claire.
Okay, cool. Super.
Awesome. Thank you.
Okay. How's that look? If you can see it, let me know so that then I'll start.
We can see it, Claire. Please go ahead. Thank you.
Okay. Okay. Thank you very much. I am extremely pleased to be a part of celebrating Joey Comiso's 80th birthday and decades-long career. And I thank both Gay and Cynthia for organizing this symposium and inviting me to participate. I've had the privilege of knowing Joey since July 1978, when I began work at NASA, Goddard Space Flight Center, over 42 years ago. Joey had already been at Goddard for about a year at that time. And within weeks of my arrival at Goddard, Joey and I were working together on a project led by Jay Zwally to obtain sea ice information from the first U.S. satellite passive microwave imager. And our work started with the Antarctic sea ice. And then after years of working on the Antarctic sea ice, we turned to the Arctic sea ice. Since then, Joy and I have both worked extensively on both Arctic and Antarctic sea ice studies using satellite data. And this talk will emphasize the Arctic work, and particularly the work that we have worked on together. So next slide here. I know that there are several sea ice speakers today, but there are also people who are not sea ice experts. And so since I'm on first, I'll give some introductory sea ice descriptions for those in the audience who are not experts in sea ice. So here's some photographs of sea ice from the Arctic, and just to indicate the variety of sea ice. Sea ice is ice that's formed from seawater, and sometimes it's thin scattered flows, sometimes it's much larger, more substantial, can easily handle helicopters and airplanes landing on it. So sea ice covers a very large area of the polar regions, and this slide shows Arctic on the left, Antarctic on the right. Green shows the sea ice cover on average over the past 40 years, and the end of summer. Well, white shows the end of summer, and green and white together show the end of winter. So in the Arctic case, the sea ice cover in the end of winter is roughly 15 million square kilometers. This is over twice the area of the continent of Australia, just to give you a sense of how much area is covered. And in the Antarctic case, the wintertime sea ice cover is even larger than it is in the Arctic case. So it covers a large area and it has impacts. And this slide shows a couple of the climate impacts on the top. So it has a high reflectivity of solar radiation, and that's very important from a climate sense because it's reflecting away much of the solar radiation that comes into it. It also is an insulator between the atmosphere and the ocean. It's got impacts on plant and animal life and impacts on human activity. So lots of impacts. And as a result, NASA, with the new satellites that it had in the 1970s, looking at the Earth and sending down a lot of data, naturally, sea ice was one of the many, many variables that they wanted to see whether or not the satellite data were going to show us anything significant about the sea ice cover. So these are two of the important satellites that were launched back in the early 1970s, the first Landsat satellite on the left and the Nimbus 5 satellite on the right. The Landsat measures invisible radiation, the type of radiation our eyes see, whereas there's an instrument on the Nimbus 5 satellite that measured microwave radiation, and that became very important for both me and Joey. Here are two pictures from Landsat visible imagery, and you can see on the left that it's terrific in terms of seeing sea ice just the way you would expect sea ice to be if it's a clear day out with sunlight. The problem is it's often not a clear day. There are often clouds in the way, and so you get pictures like that on the right, and also sometimes it's dark out, and therefore you would not get a picture from the visible imagery. And so as a result of those limitations, we tend to look at microwave data more frequently than the visible data for the climate studies. And the microwave data have three really important characteristics for getting sea ice from satellites. And one is that sea ice has a very different microwave emission from water, liquid water, and that helps us distinguish ice from water in the satellite microwave data. And then the two other huge pluses are that the microwaves are coming from the Earth system itself, therefore sunlight is not needed. We can get data whether it's dark or light out. And then the other really important one is that the microwaves, if you pick the right microwave wavelengths, it can go straight to the clouds. And so therefore we can get our data even if it's cloudy out. So there were a group of us that were involved in trying to figure out how to take the microwave data and get it into giving information about sea ice. And as I mentioned, Jay Zwally was heading the group when Joey and I first arrived. Joey and I were very much involved in this study from the beginning of when we were there. And then the other four were Per Gorson and Bill Campbell, both of whom are deceased now. Frank Carsey, who left Goddard in the early 1980s, and Don Cavalieri, who retired several years ago. So that was the group of us, and this is the type of data that we were looking at, and the black indicates missing data. The quality of the data was nowhere near what we get now, but this was state of the art then. I mean, this was a mission that was planned to try to see, will microwave information tell us something about the Earth? And these microwave data ended up telling us a lot about the sea ice cover, and other groups at Goddard were looking at all sorts of different things with these data, like vegetation and sea surface temperature and other characteristics. So it certainly proved to be valuable. We ended up producing two books. One Jay Zwally led, and that was for the Antarctic ice. And then when we switched to the Arctic ice, I became the leader of the group. And so, and in both cases, the second author was Joey Comiso. And in both cases, his contributions were vital to the success of these, getting these two books out. Now, that work was all with the Nimbus 5 electrically scanning microwave radiometer, ESMA. That gave us a 4-year record. And unfortunately, that 4-year record ended before the next major passive microwave instrument was launched, and that was on the Nimbus 7 satellite. Since then, since the launch of Nimbus 7, which was in October of 1978, since then, we have had a close to continuous record from the microwave data. So we have over a 40-year record now and can really see a lot of changes in the Arctic ice from this data set. And this shows a sample from last year, just showing the March and September ice covers. March is when the ice cover is the most extensive in the Arctic, and September is when it's the least extensive. So you can see from here the comparison between most extensive and least extensive. So clearly, when you plot monthly averages, what's going to really be most apparent is that there's a huge annual cycle with way more ice in the winter than in the summer. So we also do yearly averages in order to get a better sense of the trends that might be there. And Don Cavalieri and I published a paper with these two figures in it. And as you can see, there's a slight downward trend, not convincing at all in terms of a long-term trend. It's only a few years here, but it was the record from the Nimbus 7 data, and this was published in 1989, and this was a time frame in which people were becoming more concerned than they had before regarding global warming. And so it was clear that even though this was not convincing data at the time, it was clear that this was a record that we really should put an effort into continuing. And since the Nimbus 7 mission ended in 1987, we had to switch to the follow-on passive microwave instruments, which happened to be from the Department of Defense. And so we switched to theirs, and the group of us took quite an effort to match the two data sets. So from the SIMR and from the SIMR was the instrument on SSM on Nimbus 7, and then the SSMI is the instrument on the DoD satellites later. So we took a lot of effort to get those data sets matched. And then in 1999, we published a paper, and this was a group of me, Don, Joey, Jay, and Per. So the five of us published a paper with showing the Arctic sea ice extents, and these are the monthly averages for 1978 through 1996. And as you can see, it's the seasonal cycle that just dominates the picture. So we took the seasonal cycle out by doing monthly deviations, and then the picture becomes much more clear in terms of the trends. And so here you can see that the trend was quite clearly downward, much more convincing than the 1989 paper. And not only was it more convincing, but roughly the same time, a group from the University of Washington, led by Drew Rothrock, published a paper from submarine data looking at the thickness of the ice, and ended up coming out with the ice having thinned quite substantially. They had a 40% decrease, which was later amended when they got more submarine data to look at. And so it was reduced to 32% in the amended results. But still, the key thing was in this roughly the same time, two important papers came out, one from Goddard saying that the extent of the Arctic sea ice had decreased, and the other from the University of Washington from submarine data saying that the ice had thinned. So the combination of the satellite data for the extent and the submarine data for the thinning was really powerful, and this got a lot of press at the time, and I think contributed to what became pretty soon thereafter, sea ice became like a poster child of global warming issues. So this is what the picture looked like in the monthly deviations up through 2007. I put this one up because of how dramatic the decline is in 2007. This was so far beyond anything that any of us in the sea ice community had expected or had seen before. And as a result, Joey and I decided, well, we would try to figure out why this decline was so great. If you look at the image at the bottom, I'll just point out how easily you could have done a northwest passage that year. So Joey and I worked on a paper, it was led by Joey, and we determined that this remarkable decrease was a combination of the atmospheric conditions, higher than normal temperatures, and the winds happened to be favorable to reducing the ice cover, but also the preconditioning of the ice. We figured the same atmospheric conditions would not have led to the same result if the ice hadn't already been thinned quite a bit from the previous years. So then the ice rebounded a bit after 2007, but in 2012, it went down even further than it had gone down in 2007. So Joey and I decided again that we would look into this. And so we wrote a paper published in GRL in 2013. And again, we found that the atmospheric conditions were particularly conducive to reductions of the ice. So in that case, too, we concluded the combination of atmospheric conditions and preconditioning of the ice. The ice has not gotten down again to the level that it was in 2011. Right now, it's like second lowest now in 2020, but it has not gotten down to what it was in 2011. And this shows the full set of monthly averages from November of 1978 up until the end of last year. And this shows the monthly deviations and the yearly averages. And as you can see, the Arctic ice is definitely decreasing quite a bit. And in fact, the 55,000 square kilometers per year on average trend, that means that within 6 years, the Arctic on average loses more ice area than the area of the Philippines, just to give a comparison there. We do update, and this is an effort led by Joey. We do update every week on our website what both the Arctic and the Antarctic conditions are like. So this just shows a sample of two of the images from there, and the 2020 is in red, and you can see it's not as low as the 2012 situation, but it is lower than any of the others. So Joy and I have also compared whether the results would be different, whether you're using a different algorithm or whether you're using different passive microwave sensor. And I'm not going to go into this in detail because of the time here, but we concluded that the basic results remain the same. The specific numbers differ, but the basic results remain the same, and the numbers are fairly close. So some closing thoughts here. I'll mention also that Antarctic has been very different from the Arctic. The Antarctic case, the ice was increasing for much of the period until 2014 and then plummeted much more rapidly than the Arctic decreases, but just for that period of a few years, 2013 2014 to 2017. And then it's rebounded a bit since then. So the Antarctic case is more a case that we don't really fully understand. The Arctic case is much more understandable. We expected decreases because of warming, and we expected that the decreases in the ice would contribute to warming too. So the Arctic case is more in line with the expectations. And in view of time, I'll simply say that Joey and I both have done lots of other work, both on sea ice and on other things. I've looked like at the length of the sea ice season and the global sea ice cover. Joey's looked at things like the multi-year ice and temperatures of the ice and other things. And both of us are continuing to work on these efforts. And this is my last slide. And basically, I want to say thank you to Joey. Congratulations on your 80th birthday, but thank you for your 4 decades of work at NASA. Thank you for your friendship. Thank you for being such an inspiration in the work that you've done in your original home country of the Philippines. Thank you for bringing such impressive young Filipino scientists as Gay Perez and Cynthia Garcia to spend time at Goddard. So thank you. And thank you also to Gay and Cynthia for organizing this symposium. That's it.
Well,
Thank you
very
so much, Claire. Okay, so thank you so much, Claire.